In this section, we're going to look at lines and planes in three-dimensional space. The most efficient way for us to write the equation of a line or a plane in 3D space is by using vectors and the parameter t. So let's first look at lines. Given any line, all we need is a point, and here we're going to use the point p sub 0 or p naught. All we need is a point and a direction vector, and our direction vector here is the vector v. Once we have a point and a direction vector, then given any t values, we can get our whole line. So imagine changing this to vector form. We can take any vector from the origin to our point P sub 0, and that vector, which we're calling r naught or r sub 0, will correspond to our point P. Now we have our direction vector, so imagine multiplying the direction vector by some t values. And as we multiply the direction vector by t values, what we're doing is we're scaling it. We're changing its length. So as these t values get larger and larger, our direction vector will end at all the points on this line. And now we can use negative values for t as well. If we multiply by negative values, we'd be going in the opposite direction. So that's the basic idea of changing a line in space to vector form with the parameter t. In the box below, we'll find the definition of that line in vector form. So all we need here is a point, and we need a direction vector. Once we have those, then we can write the vector form of an equation of a line in space as the vector r equal to r naught, which corresponds, a vector corresponding to p naught, plus t times our direction vector v. Or in other words, it's going to be the vector x naught, y naught, z naught plus t times the direction vector abc. Since this is a complete line, our t values are going to go from negative to positive infinity. What's really nice is notice that if you do distribute the t and you combine those two vectors, what you have is the equation in parametric form in 3D space. So we have our x value as x naught plus a times t, and then we have our y value and our z value. Example 1, we want to find the equation of the line that is passing through the point -1, 2, 5, and it's going in the direction of this direction vector v. So the -1, 2, 5, that would be our x sub 0, y sub 0, z sub 0, and the vector v would be the a, b, and c in the equation. So the equation of our line, I'll call it r of t. Remember, it's a vector equation. It's going to be the vector corresponding to our point, so -1, 2, 5, plus t times our direction vector, which is 2, 3, -5. Now, in your MyLab, it may be that you can leave your equation in this form. Sometimes they don't have you combine it. I personally like to combine it to have just one vector. So notice if I were to distribute the t and combine those two vectors, I would have a -1 plus 2t. The next component would be 2 plus 3t. And then the last component would be 5 minus 5t. Now you don't have to write this, because if it's not written, we'll assume that the t values will just go from negative to positive infinity. But I tend to write it anyway. So notice that if I have it in this form all combined, then you can clearly see what the parametric representation is, because the first component, that's your x value. So x is equal to -1 plus 2t, y is equal to 2 plus 3t, and z is equal to 5 minus 5t. Again, oftentimes MyLab won't have you combine it. You could just leave it in the first form. Something to keep note of is that this is an equation of the line. it's not unique. Remember, whenever we're parameterizing, oftentimes we'll have infinitely many ways to describe the same object. Example 2, we want to find the equation of the line that's passing through 2 points. So the issue I have here is I don't really have a direction vector. However, I know that my line is going to pass through these 2 points. So my direction vector v can simply be the direction vector from P to Q. Remember, when we compute that vector, it's always Q minus P. So the first component, 4 minus a negative 2, gives me a positive 6. The next one would be a positive 1, and then a negative 8. So that would be my ABC. And I can arbitrarily choose P to be my starting vector x naught, y naught, z naught. The equation of my line is simply the vector -2, 0, 7, plus t times the direction vector, which would be 6, 1, negative 8. Now remember, this is not unique, and since it is a line, my t values are going to go from negative to positive infinity. Okay. Example 3, we want to find the equation of a line segment from P to Q. So we have to be careful because this is not a complete line. This is just a segment of a line, and it has a specific direction. It's going from P to Q. So when I find my direction vector, it's going to start at P and then go to Q. So this is similar to something we did in two-dimensional space. So first of all, I need my vector from P to Q. And again, that's Q minus P. So when I take Q minus P, I get 4 minus 1, so 3. And then negative 5, negative 1 minus a negative 5, so that would be a positive 4. So I have my direction vector, and it's starting at P, so that would be my x sub 0, y sub 0, z sub 0. And my line segment is going to be 1, 6, negative 5, that's my starting point, plus t times 3, negative 5, 4. Now remember, this is a line segment, not a complete line, so my t values are not going to go from negative to positive infinity. I have to figure out my starting t value. Notice that if t is equal to 0, I am at my starting point. And when t is equal to 1, I'm at the point 4, 1, negative 1. Okay, well, let's just say that I couldn't see that. How would I algebraically solve for those t values? Well, the point that I want to get to, it's clear that to get to the starting point, all I have to do is put in 0 for t, because that first vector is the starting point. So if I want to know what t value to get to the ending point Q, then I know my goal is to get to 4, 1, negative 1. So the first component is 4. And if I were to combine this and do 1 plus 3t, I know that that first component, 1 plus 3t, I know that that has to equal 4. The next component I need to get to, that y value, is a value of 1. And I know the equation is 6 minus 5t for my y value. And then my z value, I need to get to negative 1. The equation I have is negative 5 plus 4t. So all I have to do is set my x, y, z equal to my q values and solve for t. So when I subtract the 1 and divide by 3 in the first component, it's going to be t is equal to 1. And these better all be the same, and they are. If they are not the same t values, then the math is not correct, and you have to double check your calculations. So this would be the equation of the line, and I didn't combine it, but I could. So this would be the equation of the line segment from P to Q. The first component be 1 plus 3t. The y would be 6 minus 5t. The z is going to be negative 5 plus 4t. Again, my t values are going to go from 0 to 1. Since it's just a line segment, I need to specify that. In example 4, we want to find the equation of a line through a point, but we know that this line is going to be parallel to this other line that I have. So since they're parallel, I can use the same direction vectors. So notice that the line that I was given, if I were to decompose it and split it apart, would pass through the point 0, negative 9, 0, plus t. The direction vector is always the coefficients on the t value, so this would be 5, 3, and negative 4. So now my direction vector would be the 5, 3, negative 4. That's my direction vector ABC. The equation of my line is going to pass through the point negative 1, 0, 5, so that's my vector negative 1, 0, 5, plus t times the vector 5, 3, negative 4. And that's it. Again, it's a line, so if I want, I can specify that my t values are going to go from negative to positive infinity. Something else I can do is I can find a distance between a point and a line using this formula that we have here. So if you have any point Q and you have any line written in vector form with parameter t, to find the distance, I simply take the magnitude of the cross product of the direction vector v with the vector pq, and then I divide by the magnitude of v. So p is any point on our line, and again v is the vector parallel to the line. Let's find the distance between this point q and the line. This line is given in parametric form, x, y, and z. So first of all, I need, in the formula, I need my direction vector v, but I also need to find the vector pq. I have q. How do I find p? Well, let's look at the parametric representation. My point p is going to be equal to, and if we look at x, it's 3t plus 7. 7 is the x sub 0. Y is 1 minus t. So remember, you're looking at the number part, not the t part. So that would be a 1. Z is 4t plus 5, so the 5. So I have my point P, which is 7, 1, 5. Now the vector v is simply the coefficients on the t values. That would be the vector 3, comma, negative 1, comma, 4. So I need to take the magnitude of the cross products over the magnitude of our vector v. First thing I want to do is I want to find my vector pq. So remember, that's q minus p. So negative 4 minus 7 would be a negative 11. 2 minus 1. 7 minus 5 is 2. I have all my pieces. The distance is going to be the magnitude of V crossed PQ over the magnitude of V. The first thing I want to do is I want to compute the cross product. So remember, when we do our cross products, we have to do it in a specific order. It's the order that it's written. So we're going to have an I vector, a J vector, and a K vector. Sorry, I'm trying to write too fast. Where the I vector, I, J, K vector is our V vector. It's got to come first. So we have the 3, -1, 4. And then the PQ would be the -11, 1, +2. The first component is ignore column I and do the cross product for the JK. So that's going to be -2 - 4. And that would be our I component. So it's always plus, minus, plus. So it's going to be a minus. Cover your J column and do your cross product. So that's going to be 6 minus -44. So that's 6 plus 44. J plus, cover the K column. It would be 3 minus 11. Or in other words, this is going to be our vector -6, -50, and -8. Double check me on my math. So our distance is going to be the magnitude or square root of -6 squared plus -50 squared plus -8 squared over the magnitude of our direction vector. That would just be the square root of 3 squared plus -1 squared. I never make my bar long enough. Plus 4 squared. When I computed this, I got 10. And that's just by accident that it came out that nicely. Okay? So that would be our formula for direction. And now let's move on to planes. And that was just a direction from a point to a plane. So this is the idea when we're defining a plane in space. First of all, we're going to need to have a point on that plane, and it could be any point. Here we have this piece of 0 or P0. So think of any point on the plane. Take any other point on the plane and draw a vector. Any point at all in the plane, draw a vector from your starting point to any point that's in the plane. Notice that if you take all the points in the plane and you draw a vector from your initial P0 to that point, imagine that all those vectors sweeping around would form a plane. So what all those vectors have in common is they're all going to be perpendicular or orthogonal to the normal vector at that point. And it could be any normal vector at that point. The length doesn't matter. And even the direction really doesn't matter. It could go in the opposite direction and it would still be any normal vector to that initial point would be the way that we define a plane in space, which is what we have in this box here. This would be the general equation of a plane in three-dimensional real space. You need a point, and you need a normal vector, which we'll call ABC. If you have a point and a normal vector, then you get the following equation. You get A, the normal vector, coordinate A, times an x value minus x0, which comes from that initial point, plus B, y minus y0, plus C, z minus z0, equal to 0. Now, if you were to get rid of the parentheses and combine like terms, you would have a more general form ax plus by plus cz is equal to d, where d is going to be this number a times x naught plus b times y naught plus c times z naught. Okay, so if you were to change d, the d value, what's going to happen is you'll just get a family of planes that are going to be parallel to your plane. So all parallel planes have not same normal vectors, they could be different normal vectors, but they're all going to be in the same direction. So let's find an equation of a plane that's passing through a point with a normal vector 2, 1, 2. And all we have to do is simply plug those values into our equation and then simplify it. The next part is find the intercepts and sketch the graph of the plane. All right, so we have our point 1, negative 4, 7, and we have our normal vector. So remember the 2, 1, 2, that's your A, your B, and your C values. And then this would be x naught, y naught, z naught for that p value. I have 2 times x minus 1 in parentheses plus, and here it's just 1 times in parentheses y plus 4. Don't really need the parentheses. Plus 2 would be my c value, z minus 7. And then I set that equal to 0. So that's the general equation of the plane, but then I want to get rid of the parentheses, combine like terms, and so on. So we have 2x minus 2 plus y plus 4 plus 2z minus 14 is equal to 0. So if we take the negative 2 plus 4 minus 14, that's going to give me a negative 12, add it to both sides, and I get 2x plus y plus 2z is equal to 12. And that would be the equation of my plane. Now I want to go ahead and sketch the graph. So all I have to do is find my intercepts. And here this is x, y, and z. So let's find our intercepts. The x-intercept is found by letting y and z equal 0. So that would just be 2x equal to 12, or x is equal to 6. So the x-intercept is the point 6, 0, 0. And I'll just pretend like 6 is around here. My y-intercept, all I have to do is let x and z be 0, and my y-intercept would be at y is equal to 12, or 0, 12, 0. And I'll pretend like this is 12. My z-intercept would be when x and y are 0, so we have 2z is equal to 12. Z is equal to 6, that would be the point 0, 0, 6. And then this would be my sketch of a plane, where all we have to do is draw a line through our intercepts, and we're done. Just a sketch, doesn't have to be perfect. For example 7, it says find the equation of a plane through the 3 points P, Q, and R. The problem is I don't have a normal vector. However, I know that if I have 2 vectors and I cross them, their cross product gives me a normal vector. So all I have to do is take these points, decide which is going to be my P sub 0, and might as well just take this first point P and call that P sub 0, and get 2 vectors with the same starting point. So I could define vector PQ, and I can define vector PR. Remember, same starting point. And then when I find those direction vectors for PQPR, then all I have to do is take their cross product and I'll get a vector that's normal to those. So PQ is going to be Q minus P. So that looks like it would be 0, -6, -3. PR would be R minus P. It looks like that would be -1, -3, and -2. So my normal vector is simply the cross product of my I, J, K of 0, -6, -3, and then -1, -3, -2. So the vector I get if I cover the I column would be the -6 times -2. That would be a +12. -9 would give me a +3. I'm skipping all the scratch work. Cover the J column. It looks like it's going to be 0, -3, but it's a minus, so it becomes a +3. Cover the K column, I get 0, -6, so -6. So this is a normal vector. Now, here's the fun part. Notice that each one of those components or coordinates has the common factor of 3. So I could simply factor out the 3. I'm left with the vector 1, 1, -2. That's also a normal vector that I could use. Multiplying it by 3 just makes it longer, but it doesn't change its direction. And I think I'm going to use this normal vector because it's got a 1 and a 1 in it. Those are really nice numbers. So the point I'm using is 1, 2, 3. Here I have 1 times x minus 1. And then the b is going to be 1, so it's going to be plus 1 times y minus 2. And then the last one would be a -2, so it's going to be -2 times z minus 3 equal to 0. So I get x minus 1 plus y minus 2 times z plus 6 equal to 0. X plus y minus 2z is going to be equal to -3, I believe. And that would be the equation of my plane. And let's look at another example, example 8. Let's say that we have a plane, 3x plus y minus z equal to 6. And we're going to go ahead and answer parts A through D. Part A says, find a vector that's normal to this plane. Find the intercepts. Find the equations of lines where the planes intersect the coordinate planes, and sketch the graph. Part A. Ooh, I don't like that color. I want it to be blue. So part A, the normal vector, is simply the coefficients on the x, the y, and the z. So that would be the vector 3, 1, -1. B. Find the intercepts. Well, we know that all we have to do to find the intercepts is to set the other values equal to 0. So the x-intercept would be 3x equal to 6. So x is equal to 2. The y-intercept, if we set x and z equal to 0, we have y is equal to 6, so that would be the point 0, 6, 0. And then the z-intercept would be setting x and y equal to 0, we get negative z is equal to 6. So z is equal to negative 6. That would be the point 0, 0, negative 6. So we found the intercepts. C. Find the equations of the lines where the planes intersect the coordinate planes. Okay, so xy plane, that would be where z is equal to 0. If we set z equal to 0, the resulting line is a line in the xy plane. So that would just be 3x plus y equal to 6. And that's all we have to do. To find the line in the xz plane, we're setting y equal to 0. And if we set y equal to 0, I get 3x minus z equal to 6. And then in the yz plane, we're letting x equal 0, which gives us y minus z is equal to 6. So the final part, D, is to sketch the graph. And, I got some negative values in there. So let's see, we have 2, 0, 0. I'll pretend like this is at 2. I have 0, 6, 0. I'll pretend like this is 6. But the z-intercept is 0, 0, negative 6. So if I go down to negative 6, and then draw my lines, and I'll do those in green. Draw all the lines passing through these intercepts. These would be the equations of the lines in the different planes. If I had to label these, let's see, this would be 3x minus z is equal to 6. Okay, that line that looks horizontal would be the 3x plus y equal to 6. And then we have y minus z equal to 6. Okay, so that's it for that problem. This last page is looking at properties with intersecting planes or parallel planes. So if we look at these diagrams, notice the first diagram, we have two planes that are parallel. And if you have two planes that are parallel, what happens is their normal vectors will also be parallel. So if you have parallel planes, they have parallel normal vectors, which means that their normal vectors are going to be multiples of each other, because remember that's what parallel means with lines, is that they are scalar multiples of each other. Let's say that you have the second diagram where the planes are actually perpendicular or orthogonal. What happens is if you have intersecting planes that are orthogonal, then their normal vectors are also orthogonal. So orthogonal planes have orthogonal normal vectors. The property here is that their dot product is going to be equal to 0. So going back to dot products. The angle between intersecting planes here, this last bullet, is defined as the acute angle, so the smallest angle between their normal vectors. So to find that, you would just use the definition of a dot product, because that has cosine of theta. So all you would have to do is divide both sides by the magnitude of the two vectors and then take cosine inverse. In example 9, we want to determine if the planes are parallel or orthogonal. If the planes are orthogonal, find the line of intersection. So notice that in our diagram, the second diagram, if we have two intersecting planes, they're going to have a line of intersection. Alright, so I do have these two planes. The first thing I want to do is I want to find the normal vectors for the two planes. So this first plane will give me some normal vector. I'll call this n sub 1, and it's a vector. Remember, that's just the coefficients on x, y, and z. So this vector will be 2, negative 3, 6. And then in this second plane, I'll call their normal vector n sub 2. Coefficients would be 3, 4, and 1. So I have these two normal vectors. Are they multiples of each other? Because if they are multiples of each other, then these planes are parallel. But if I look at these two normal vectors, there's nothing that I can multiply by 1 to get the other one. So since they're not multiples of each other, they're not parallel. Next thing I want to do is I want to check to see if these planes are orthogonal. So if they are orthogonal, then their dot product has to be equal to 0. When I take the dot product of 2, negative 3, 6, dotted with 3, 4, 1, whoops, helps if I have an equal sign. Well, that's going to irritate me. Then I get 6 minus 12 plus 6, which is equal to 0. So these are orthogonal. So the first part of the question is to determine if the planes are parallel or orthogonal. In this case, they are orthogonal. It could happen that they're neither. So if they are orthogonal, then they're going to intersect, and their intersection will be a line. I need to find the equation of that line. So if I'm finding the equation of the line, what I'm going to need is, I'm going to need a normal vector v, but I'll just use n. And I need a point. Okay, so I need a point and I need the direction vector. Okay, so to find a point that they have in common, the two planes, I could simply set them equal to each other or solve the system of equations algebraically. The problem I'm having is that I have two equations, but I have 3 variables. So algebraically, I'm not able to solve it. So instead, I'm going to do this little trick. I'm going to either take the x, the y, or the z and just let it be 0 and see what happens. So to find the point, a point that these two planes have in common, because that will be a point on my line, I'm just going to arbitrarily let x equal to 0. Because once I do that, then I've got 2 equations with 2 variables, and algebraically I know how to solve that. So if x is 0, I have one equation that's negative 3y plus 6z equal to 0. And I also have another equation, which would be 4y plus z equal to 1. I could take the second equation maybe and solve it for z, going back to our algebra techniques. This is not the only way. Maybe write z equal to 1 minus 4y, and then take that z value and plug it into the first equation. If I do that algebraically, again, I'll have negative 3y plus 6 times my z value is now 1 minus 4y equal to 0. So I have one equation, one variable that I can solve for y. I have a negative 3y plus 6 minus 24y is equal to 0. So it looks like it's going to be negative 27y is equal to negative 6. So it's not nice, but I can still solve for y. It's going to be negative 6 over negative 27, which would be 6 over 27. I could reduce that, I guess, by 3, but I think I'm just going to leave it this way. Maybe not. It's going to irritate me. I'm going to reduce this to 2/9. Okay, so now that I have my y value, I'm going to plug that y value into the equation for z and get z is equal to 1 minus 4 times 2/9, so that would be 8/9. So z is going to be equal to 1/9. And remember, I already set my x value at 0. So I have this point 0, 2/9, 1/9. And I can plug that point into both of my equations for my planes, and I'll find that this point will be a solution to both equations, so this point is on both of those planes. So that's a point that they have in common. There's infinitely many points. This is just one. Now I need my normal vector. Well, going back to these diagrams, necessarily, if you have planes that intersect and the vectors are also normal, think about this line, and I'm going to do this in a different color. Let's say that we have this line of intersection. If I take this normal vector and move it down, take the other normal vector and slide it down. Oops, if I could draw this. Then necessarily these vectors, since they're normal to each other, they're also going to be normal to that line. So if I take the cross product of these two normal vectors, n sub 1 and n sub 2, then I'll get the normal vector for my plane. Let's see, why don't I do that here? So take the cross product of n sub 1 cross with n sub 2, and it doesn't matter the order that I'm crossing these vectors, because it doesn't matter if the direction of the normal vector is going up or down, I guess would be the easiest way to describe it. It's still going to be normal. So my ijk would be that n sub 1 is 2, negative 3, positive 6. The n sub 2 is 3, 4, 1. When I cross these two, maybe I won't show all the steps. You guys can check me on my math. I'll just write it out here. Covering the I get negative 3 minus 24. So that's a negative 27. And it looks like covering the j, I get 2 minus 18, so positive 16. Cover the k, I get 8 minus a negative, so 8 plus 9, positive 17. All right, I have a line with a direction vector and a point. So the equation of my line is going to be r of t equal to the point as a vector 0, 2 over 9, 1 over 9, plus t times this direction vector, negative 27, positive 16, positive 17. And again, I could stop there, or I could combine it all. I think I'm just going to stop there. And I don't have to put the t values from negative to positive infinity, because if I don't write it, it's assumed the t values go from negative to positive infinity. Okay, so that's it for this section on lines and planes in space.